Discovery's 4 computers now have primary control of critical vehicle functions.
Welcome to this English edition of IDA Space Talks. IDA Space Talks is a Danish podcast focusing on everything space-related. The podcast is published in collaboration with the Danish Society of Engineers, IDA, and the professional network IDA Space. My name is Tino Tønnesen, and I'm your host in IDA Space Talks. In this episode, we're heading above the clouds, to the strange electric world where storms reach into space. When Danish astronaut Andreas Mogensen first captured flashes of deep blue light from the International Space Station, it opened a new chapter in lightning research. To help us understand what really happens up there, we are joined today by senior researcher Dongshuai Li from DTU Space. She is one of the scientists studying these mysterious upper atmospheric flashes and developing new technology to capture them in action. Welcome, Dongshuai.
Thank you, Tino. It's a great pleasure to be here. I'm Dongshuai. I'm a senior researcher from DTU Space. As mentioned by Tino before, the blue electron discharge has been the main topic of my current research. And I have been studying atmospheric electricity and lightning physics for more than 20 years.
Everyone in Denmark knows about the lightning because of our famous astronaut. He took photos of them. But Dongshuai, what actually happens above the clouds?
Yeah, most of the lightning we see in our daily life is the lightning occurred between the cloud and the ground. We call it cloud-to-ground lightning, the CG lightning. And also another part of lightning is occurred, most of part is inside the cloud, we call the intra-cloud lightning. But there's a very mystery discharge nearby the cloud top, we call it cloud top discharge. That's the part has been studied only in the recent years and discovered by our astronaut Andreas. And before that mission, we know very, very little knowledge about it.
Yeah, it's lightning going upwards.
Yeah, it's a lightning going upwards directly from the thundercloud top, from the tropopause to the upper atmosphere. It's the different type of lightning, but of course they are all electron discharges.
And was Andreas the first astronaut who ever noticed these strange flashes of blue light?
Yeah, it's during his first mission. I think it's 1 week mission on the ISS. And he's using a Nikon regular camera and point outside of the cupola windows and try to capture about lightning. And all of a sudden, they saw this upward blue electron discharge. The blue discharge occurred from thundercloud top. And they are very short-living transmission phenomenon. And then they have these very special blue colors. And they occurred in a very localized region. And in the very fast rates, like around 120 per minute.
Really?
Yeah. He recorded a lot of them. But by the time we don't know actually the physics behind it.
No.
Yeah, we know very little about it. And we thought it's very rare. It's a very rare discharge activities. And we don't know, are they going to affect the upper atmosphere? It is something that, different from the normal lightning that we understand related to thunderstorm. Mm-hmm. And then inspired by this discovery, there's a mission called ASIM. It's also led by DTU Space from Denmark.
ASIM, yeah.
Yeah, and it launched from 2018. And ASIM actually discovered this phenomenon actually occurred not just rarely, it occurred globally.
Okay, and ASIM is the Atmosphere Space Interactions Monitor.
Yeah, ASIM is a module on the ISS.
Yeah.
It has been launched in 2018 and is still operating right now on the ISS above our head.
Okay.
Yeah, it includes 3 photometers covering the particular bands which can look into the inner plasma physics of lightning. And of course, ASIM is also targeted to the upper atmospheric phenomena. We call it transient luminance events.
Yeah, that's the TLEs.
Yeah, the TLEs. Yeah. Yes, that's right. And it also includes the cameras. The major difference from ASIM comparing to the other lightning imagers on the satellites is that ASIM, the sampling rates, the sampling frequency of ASIM is much, much higher.
Yeah.
It's in 100 kilohertz.
Oh, really?
Yeah, it's like 10 microseconds. If we talk about these transient luminous events, the TLEs, the duration for them is like in the milliseconds. So if you want to really look into the physics behind them, you have to reach to the scale of the microseconds.
Of course you have, yeah.
Yeah.
It sounds very difficult.
It's very difficult. ASIM is the first instrument who can reach this high temporal resolution. That's why ASIM discovered this very fascinating blue electron discharge from the cloud top.
So now we got the DTU equipment on the ISS, and Andreas had put focus on the blues, as you call them. What have we learned about them now?
There's a lot of things still unclear. Let me start with the inner plasma physics of lightning. Maybe people will understand it better. Because if you think about the lightning, it's a very bright electron channel. But if you look into the inner plasma physics behind it, it includes a very luminate channel, hot channel. We call it leaders. And it also includes some fine weight filaments, we call it streamers.
Mm-hmm.
And by using the different band of ASIM, we can actually separately identify the different modes of lightning, this inner plasma of lightning.
Yeah.
And for these blues, when we check about the photometer signals detected by ASIM, we saw they are emit very strong blue emission with very little and weak red emission involved. So it's like the very intense blue emission, but very little red emission, which indicates the physics behind it is actually a streamer-dominated phenomenon. There's no hot lightning leaders related to these so-called upward channels. It's only like streamers, very fine. That's why for many years we thought they are rare and it's difficult to observe them from the ground because the atmospheric absorption and attenuation, and we cannot observe them very easily from the ground. So the best way to observe them is from space because we can avoid this thick atmosphere.
Yes, of course, it's easier.
Yeah. So it's just like this. And then right now we know they are not just a rare phenomenon. They occurred globally, has a very similar distribution, just like the global lightning. And most part of them is located in the tropical region, of course, and gradually decreased by following the latitude.
Why is it in the tropical regions?
Yeah, because the tropical region had the most thunderstorms.
Okay, yeah. So it is related to thunderstorms.
Yeah, it is related to thunderstorms. Yeah, it's still the electron activity is related to thunderstorms. And the thing is because they occurred in a much higher altitude compared to the normal lightning.
Mm-hmm.
So they have much more effect, like the chemical effect, the radiation effect to the upper atmosphere compared to the normal lightning.
Do they affect the upper atmosphere in some way?
Yeah, they affect the atmosphere, can change, for example, the ozone layers, the NO2, the NOx, all these chemical effects related to the upper atmosphere.
Okay.
And for me, the most interesting part for them is, by studying the physics behind them, how the leader and streamer interruption in this phenomenon.
Mm-hmm.
It give our clear view how to explain how lightning actually initiate inside the thundercloud. Because when we think about how lightning initiates in thundercloud, we don't know because it's all the things is covered by the thundercloud itself. We couldn't see.
No.
It's like if you take the X-ray from the hospital, right?
Yeah.
You couldn't see like all the things surrounded by the cloud. But for this blue discharge, they coming up from the cloud top. There's some part of them, the majority part of them, is exposed outside of the cloud. And we can clearly see the transition between the streamer and leaders in this phenomenon. That gives us a natural source to study how lightning initiation actually. And another interesting point I found is really interesting because this blues has a really close correlation with the convection activities of the thunderstorm. So all the draft pushing all the particles and aerosols in the upper atmosphere. And in these regions, it's always the feeble regions where the balloons can occur.
Okay.
So by studying the balloons, it can serve as a much better indicator comparing to the normal lightning, help us to track these convection regions, help us to forecast this severe storm.
So the blues will always and only occur whenever there's a thunderstorm below it.
Yeah, we could say that because it's still a thunderstorm-related phenomenon. But interestingly, we found the blues occurred in almost every developing phase of the thunderstorm.
Okay.
Sometimes it occurred at the early phase of the thunderstorm, sometimes in the mature phase where we have a very clear overshooting top of the cloud, sometimes even in the fading phase of the thundercloud.
Yeah.
So it's still like the big unknown questions. How could blues occur during this life cycle of the thundercloud? Because ASIM only passing one storm, and for within 2 minutes time, we couldn't see the entire life cycle of the storm from ASIM observation. Because the ice is just moving in the orbit. Yeah, it's only passing one location in a very few minutes. Yeah.
As I understand it, lightning needs a beginning with an electric current, then it grounds itself. But the lightning that goes up, doesn't that need like a way to get rid of the energy?
Yeah, it do needs the source. The source is actually the charge that's distributed in the upper cloud region part. Yeah, and because of these convections, it will have, we call it the mixed region, where the charge will separate it by the convection motion. And then this is all like an unclear question. Maybe there's a localized region have the charge strong enough and to generate this electro discharge and going up from the cloud top.
How big are they?
Oh, they have different sizes, and we have been give them very interesting different names for them. The blue starters, we call them, it has hundreds of meters to a few kilometers. And then the blue jet, we call it, it has sometimes tens of kilometers. And then we also have the surface blue discharge. Sometimes we also call it blue glimpse. They only have like hundreds, tens of meters high, really close to the cloud top.
Okay.
So they have a different features for these blues. But for ASIM, because ASIM observes them in the nadir. So nadir is like to look at them in the vertical direction from the top. So everything is overlapped together. We cannot identify like, are they going up for a few kilometers or are they just occurred nearby the cloud top?
No.
So for ASIM, we just group all of them and call them blue corona discharge.
Yeah.
But they have different names. I also remember some names, they call it gnomes, the pixies. Yeah.
Gnomes and pixies.
Yeah, gnomes and pixies. Yeah.
Dongshuai, tell me about the Thor Davis experiment.
Yeah, for all the blues that we want to study, it occurs very fast. It's a short-living phenomenon in the milliseconds. We really, really need a new technology which can reach to much higher rates and can study the physics behind them.
Can you explain what is a neuromorphic camera?
Yeah, so in the new mission from Andreas in 2023 to 2024, I think it's 6 months mission for him. And we discovered there's a new technology called neuromorphic imaging technology. It's also called event cameras.
Okay.
So comparing to the normal cameras that we are familiar with, the event cameras actually only records the changing part of the brightness. So for each pixels, they act individually, independently, and asynchronously.
Okay.
Yeah.
For each pixel?
For each pixels.
Wow.
And then it only triggered when it detected a change in brightness.
Okay.
So if you think about the normal camera, it triggered the whole frame, at a fixed frame rate and take pictures for one frame one by one.
Yeah.
But for these event cameras, it will not trigger anything if there's no change in the detection in the field of view.
It only activates when
It only activates
there's
when
a
it
change.
detects there's a change, there's actually change in the brightness.
Okay.
Yeah, so it gives a lot of advantage for us. For example, it can reach microsecond tempo resolution. It can save a lot of data volume. And it's also very small. It's like the GoPro size. If you think about the normal Nikon cameras, it's much larger and much heavier.
So it's the size of a GoPro.
Yeah, and it needs only low powers. So it has a lot of advantage for the space application.
Okay.
That's why in Davis' mission, and one of our PS, Olivier Chanliang, he decided, why don't we just send this kind of camera to test this technology together with Andreas and to see how does it work for space application.
So the Thor Davis camera is on the ISS now?
It is still on the ISS now. And the observation module is that we put one of the event cameras on the top of the regular Nikon camera. And both of them record the same thing together where we can compare the results and test the performance of the event camera from them. And then for the initial results that we recorded, it proved the event camera can actually work in 100K frames per second from space. And if you look at the news and the initial results published recently, you can find there's a lot of interesting things captured by this event camera. That's the first results, the first high-speed results from space based on this fascinating technology.
What has the camera captured?
Oh, the camera captured a lot of the interesting things. Like I didn't mention for the TREs, it's not just only blues. They also have the other interesting things.
Okay.
For example, sprites, we call it. It's a large streamer system, like hundreds of kilometers. It's initiate, if there's a very powerful CG lightning, cloud-ground lightning, it will change the static electric field in the upper atmosphere and generate this large range of the streamers. We call it sprite, with a very beautiful red color.
I think I've seen photos of those.
Yeah, and also it also includes ELVs that's also captured by the Thor Davis mission. And ELVs is an electromagnetic pulse also generated by the powerful lightning. And it has a radius around, the diameter around 400 kilometers.
Wow.
It has a ring shape and spans at an altitude around 100 kilometers above.
Okay.
Yeah, so all
That's
these
huge.
things, yeah, and of course it's also captured blues. And I think they also recorded one of the very interesting phenomena they call the spider lightnings.
Okay.
Yeah, so a lot of interesting things captured from this mission, and then and also regarding to this novel technology.
Okay, spider lightning.
Spider lightning. It's like a spider shape, and it's a very large lightning. Sometimes it can reach to hundreds of kilometers.
Okay.
And the different lightning channels spread in the horizontal way. It's like the different legs of spiders.
Yeah. Okay, must be beautiful.
Yeah, it's really beautiful. If you look at it from the internet, you probably can find some results there.
Dongshuai, do you use other satellites in your research?
Yes, of course. There's a lightning imagers installed the geostationary satellites.
Okay.
It's much higher than the ISS. It's in 35,000 kilometers. It's very high. But one of the advantage for this lightning imager is that it can focus on a region and continues to record.
Because it's geostationary.
Yeah, it goes stationary. And for example, the first lightning imager from Europe just launched in 2022. And it's covered the whole Europe region, including the African region.
Okay.
Yeah, and we can see the develop of the thunderstorm and the lightning in the temporal resolution of from 1 millisecond.
Really?
Yeah, and it records the lightning day and night continuously.
It still can record it from that distance.
Yeah, it can still record it from that distance. That's amazing. Yeah. And for this kind of lightning imager, it's a great tool to study about the climate change related problem and also the severe storm related to lightning.
I guess when you use a geostationary satellite, then you can see more of the Earth, and that's the advantage of it compared to the ISS, I guess.
Yes, because in the ISS, it's only passing by a few minutes.
Yeah.
And from the satellite lightning imager, you can actually track the storms.
Yeah.
In the real time, almost.
Yeah.
And it will give us a much better way to forecast them.
Yeah, so you can actually follow
a
thunderstorm and see how it moves from like North America to South America.
Yeah, you can follow the storm. How does it move from Germany to Denmark, from Denmark to Sweden? Yeah.
We would love to send some thunderstorms to Sweden. Dongshuai, tell me about the future of lightning research. What is your focus next couple of years?
Yeah, my focus of next couple of years will based on the recent grant that I got from the DFF, the Danish national funding called Neural Lightning. We are now testing this neuromorphic imaging technology from the ground observation for the natural lightning.
Okay.
The objective for this project is that we want to understand the physics behind the lightning attachment part. Mm-hmm. When I talk about the lightning attachment part, is that when there's a lightning occurred, start inside the thundercloud and propagate downward to the ground and approaching the ground. And actually from the ground part, sometimes there's upward lightning generated from the ground.
Okay.
From the chimneys, from the high-rising buildings. And then how could this upward leader to make attach and connect to the downward leader part? That's still a very big unsolved questions from our community because we don't know which way lightning will choose actually to stroke.
No.
I remember there's a story, is one of the researchers working on the high-speed observation for this lightning attachment process in Brazil. And he captured a very nice lightning attachment process. And by the time the lightning downward leader propagate, he can see the upward leader generated from the high-rising buildings everywhere because we have the lightning rod.
Mm-hmm. Yeah.
It's very sharp, has a needle-like shape. It will generate upward leader. And also from the corner of the buildings as well. And also from the chimney of the building as well. And it's basically everywhere. So where these downward leaders will attach and to stroke on the ground-based structure. Mm-hmm. Actually, none of these lightning rods helped. It's the lightning decided, okay, I will stroke on the chimney of this building and destroyed the chimney actually afterwards.
It didn't hit the rod?
No, it didn't. It just want to say, okay, I like that chimney. I want to stroke on that chimney. And it's actually a chimney related to a pizza oven.
Okay.
So at least the pizza is cooked.
So we got all the energy from the lightning.
Yeah, got all the energy from the lightning, yeah.
But we don't know why.
But we don't know why. So this project is just helping us based on this technology to understand this attachment process. We will set up the cameras nearby one of the very unique location in Europe, in Santis Tower in Switzerland.
Okay.
So it's a tower on the top of the Santis mountain in Switzerland. And it's actually one of the hot lightning stroke, one of the hot pot of lightning stroke all around the world. For this tower, every year more than 100 lightning directly stroke on this tower.
Really?
Yeah.
And no one knows why?
No one knows why. Yeah, it's one of the possible reasons because this tower is more than 100 kilometers high and on the mountain top. Yeah. You know, if there's no other peaks surrounding and this is the only peak. Yeah. And also in the Alps region, the Alps mountain region, there's a lot of thunderstorm passing by in the mountain region during the summertime.
So it's quite close.
Yeah. So and we will set up the cameras next year around this tower, try to collect more data to analyze the physics behind it.
Okay. I think you said 100 kilometers high.
Yeah. 100 meters high.
100 meters high.
Yeah, 100 meters high. 100 kilometers, that's too much for a tower. Yeah.
All these events seems like very complex. How do you work with that? Do you use AI or what kind of algorithms?
Yeah, so far we didn't use AI yet, but this technology is perfect for the AI analysis actually, because instead of outputs the frames for each timestamp, these cameras output a stream of the events. With each event has a timestamp and spatial resolution in the pixel array.
Yeah.
And so far we already did some test campaign this year during the summertime in Barcelona, Spain. And we collected some very interesting data for the natural lightning. And also we collect some observation for the spread as well.
Mm-hmm.
But comparing to the normal high-speed recording that's in our community, which can only record a few seconds in a time, these cameras continues recording. For example, for one thunderstorm process, we have more than 5 hours data waiting for us to analyze.
Okay, 5 hours.
Yeah, if we look at it manually, I think I need more students. I need more money to work on it.
Yeah, definitely.
Yeah. So AI definitely will become a tool try to identify. So where exactly is the interesting events from this 5 hours recording data?
Let me just finish with this question. All this studying of lightning from space, how does that help us understand our planet?
Mm-hmm. First of all, by following the climate change, we saw more and more severe storms occurred very frequent. Yeah. I remember the first time I came to Denmark, one of my students asked me, why do you come to Denmark? Because we don't have a lot of thunderstorm here.
No.
Yeah, but I told them, okay, I'm studying about observing thunderstorm and lightning from space. It's a global range.
It is, yeah.
So how thunderstorm is going to affect our climate, that's still an unclear question.
Okay.
But by studying lightning, because lightning has a close correlation with the severe storm, there's a way to understand how does this severe storm develop and how to track and forecast this severe storm under the climate change. And it might also help us not just only lightning, but also this upward lightning, this blue electron discharge. What is the chemical effect for them? Upper atmospheric chemical and radiation effect for them. Yeah, we want to understand them. But so far, ASIM only observed them like in a very short time passing by.
Yeah.
And only working during the night time. For the daytime, for all the observation, we still don't know what is happening there. There's still a long way to go. But as I mentioned before, as far as we can reduce the uncertainty regarding this, that's the direction of all the scientists working on our field we want to reach. Yeah.
Great. Dongshuai, thank you very much for joining me in the studio. It was very interesting to learn about your research and the lightning.
Yeah, it's a great pleasure to be here. Thank you so much, Tino.
Thank you for listening to IDA Space Talks. The podcast is one of several podcasts from the Danish Society of Engineers, and you can find all of them at ida.dk/podcast.